No, it is working. All right, cool. All right. So, first thing I want to show you all is my screen. All right, there. Oh, lovely. So, this is the average. This is the grade distribution for the last test for the multiple choice. That ain't bad. You may not see like a 66 for a physics class is not bad. Really weird sounding. I have no idea what the averages are in your other classes, but that's really not too bad. So, 66%. Now, this is without the curve. There was a 6-point curve. There's a logic behind that. I'll get to that in a bit. But for now, I want to kind of just point this out and kind of give you a sense of where is good, where is not as good. So on this graph, so the way to interpret this is honestly to look at how I've designed the grades in general for this class. So if you all look at the grade structure, you'll see that 50% of it is from effort-based assignments. The quizzes, the discussion sections, the clicker questions, and also the assignment that is due this week called the Physics I Care About. I sent out an announcement about that. I'll talk about that as well. 50% of it is basically you put in the effort. Those points should be, for the most part, free. Largely just based on effort. What that means is if we look at the test grades, that's the other 50%. And here's how that breaks down. If you get that free 50% from just effort, you put in the effort and you got that, that means if you want an A in the class, you only need to be getting above an 80% on average on the tests. 80% or above on tests will get you an A in this class. Now, that is not including any extra credit. That is not, so like, remember the clicker questions. If you do all of them, there's kind of some extra credit that comes with that. The quizzes, there's a chance for that. So this is just assuming you kind of got that flat 50. 80% or above means that you have an A in the class. And that, if you're getting an 80% or above on the test, that means you understand the physics. That's how that works out. 80% or above is indicative that you understand the physics. And I would say that's after curve kind of thing. You can consider that after curve. A 60% or above shows you have somewhat of it, like some kind of understanding. You know, if you're down near 60, it's kind of borderline, but it's still decent. Above a 60% is still fine. It's not phenomenal, but it's not bad. Above a 60% means that you have some kind of understanding of it. That's great. 70% means you have like a goodish, fine-ish, kind of like we're on that fringe. When you're around 70%, you're kind of getting near good. 80% is kind of that good, awesome. So above a 60% means you have some like understanding of it. And then kind of below that is where we start to get into the regime of something is off. There's some misunderstanding somewhere. Something is off. Now, what does that mean? Does not mean that you're a failure. Does not mean that you're going to fail my class. It doesn't mean any of those things. It means that something is off. And once you realize something's off, the next step is what do I do to change it? That's the mindset. What is off? Maybe it's how you're approaching. Did you go through the problem set problems? How did you do your studying? Did you get extra assistant? Did you go to the help room? Did you go to my office hours? Did you make use of the resources that are available? SARC, though, I have to still double check on them if they have SARC. Okay? Again, if you're getting, and then so below that, it gets, the lower you are below 60, the more of a concern it is. So that means some change probably needs to happen. Now, what does that change look like? That is different for every single person. Some people may not have done the problem sets at all. That's the easy change. Some may have done all the problem set problems, but just weren't getting it. Okay? That's a different answer. So each person has to kind of evaluate that. And if you are unsure how to proceed, talk to me. Send me an email. I can assist you in figuring out what's going on and maybe what needs to change. Okay? The first test is a great opportunity. This is kind of our first, hey, we have our quizzes. Those are kind of our weekly checks on how we're doing. This is kind of the big overall, how have you been preparing? The next test, you can expect similar difficulty. The final, honestly, will be a bit worse. Not because the final will be harder, but because the final will be cumulative, so it just has more that you have to know. That's just how, finals are always that way. But anyway, so curves. There's a 6-point curve on this. Why is it 6 points? Why is it that much? Depending on your perspective. I looked at the questions and the responses to the questions, and I identified 2 questions that less than 50% of people got right. The rest, pretty much over 50% of people got right. So those 2 questions indicate an area that perhaps I did not prepare you all well enough on. I would not call that just a difficult question per se. May have been, but generally, none of the problems I think were super mathematically difficult or had a bunch of steps. So it was some concept that we need to spend more time on. So for those 2 questions, I gave a percentage of those points. Comes out to 6 points is what I kind of landed on for those 2 questions. Okay? Now, this does not include the free response. Again, that's going to take time to grade. I will know that when I know that. Again, I'm aiming for 2 weeks from when the test was given to have those grades. I will then have to look at those, same thing, evaluate, hey, how was question 1, how was question 2, how did people answer them? I'm going to have to look at that to decide, 1, what is the grade on it, 2, if there's any kind of curve or stuff like that. My goal with curves isn't just to give points to reach a certain percentage value. If people did above, say the average was an 80% or something, and there were still those 2 questions, I would still curve it to 6 points. If the average was lower, same thing. Because at the end of the day, my goal in this class isn't to have an average grade of this. My goal in this class is to prepare you all as best as possible. And so this is my way of in my opinion, a curve should be done if the instructor has failed in some capacity. And that's how I kind of evaluate it. Which questions overall do people do poorly on? That's kind of how I evaluate whether or not I have failed you all in certain areas, and then evaluate from there. So, again, I'm pretty happy with this. If you're not happy with your grade, that's okay. But again, it's a matter of identifying what went wrong, what strategies may need to shift, all that kind of stuff. I would consider the first test to be the hardest one, not necessarily because the content was the hardest, but because it's getting adjusted to the class. The first test in any class, in my opinion, is always tricky. You don't exactly know what it's going to be like until you do it and all that stuff. So I'm optimistic that the second one will be improved. And yes, if you are on the low end of this, a question that may come into your mind, it depends on your goals. Is your goal just to pass my class? Is your goal to get a certain grade in the class? And this is a question everyone needs to answer. Withdrawal there is a deadline for that. It's, I think, a month away from now or something. That is an option. A withdrawal does not mean you failed. A withdrawal means that something went off, you need to reevaluate. If you continue on the path, you're not going to achieve your goals. So withdraw, strategic retreat, you could call it, whatever. And then, you retake the class at some later point and achieve your goals. There's no shame in doing that. But yeah, I wanted to mention this. So there's this 6-point curve, brings up the average to a 72.22, so on and so forth. Okay, any questions on the test stuff? All right, shoot me an email if you have any comments, specific questions, concerns, come talk to me, all that jazz. Next, what I want to talk about this week, so there's 2 things. There is a chance, I say a chance, it's pretty easy. I believe I sent out the announcement on this, but I'm going to have to triple check. Let's go to Web Courses real quick to check that. So, in Web Courses, I have posted a survey, and I believe I sent out an announcement on it, but I need to fact check myself on that. That's the old one. There we are. Let's see. Announcements. No. Okay. I need to send this out. I made a mention of it, but I need to send this out. So I'll send an announcement tomorrow or today or something. There's a survey on here. Super easy. Super quick. This survey is for me, honestly. So this is worth 2 bonus points, 2 percentage points on the test. Why am I making it worth points? Because I want y'all's feedback. So this is just a very quick survey for me to get a sense of how you all felt about this. So the first question, scale of 1 to 10, how would you rate the difficulty? Second question, scale of 1 to 10, how much of the problem sets did you go through? all of this, I am not going to look at individual responses. I'm going to take all of this together, like as a collective. So, like if you put that you thought the test was a 10, great. Like there's no, like that's not going to affect you in any way whatsoever. So be honest here. There is literally no downside. In fact, let me show you all how the points are given. Summary, awesome. Half a point for that one, look, it's a half a point for every single one. I don't care what response you pick, you get the points. So, just to make it clear, do not, I care, but not as far as, my feelings towards you or anything like that. I care because this is feedback from me. How much of problem sets did you go through? How prepared did you feel going into it? These may not be the same thing. That's why they're two different questions. That's what I want to test. Did that feel the same? And the last one is when you click this link, boop. Well, take me away, link. It's going to take you to an anonymous fill in the blank kind of thing. So this one does not collect any information from you, but this is more open responses. The other way, I kind of had to do the other way just to be able to give points and make it easier. This is just, hey, you gotta, you have to put something here, put a smiley face, put a well thought out response, put something, and then after you do this, it's going to give you a code to put into the other one to let me know that you did do the survey. Completely anonymous. What could I have better done to support you all? And then just any miscellaneous feedback. Okay? So this is for me. This is for me so that I can, a test is a test of me as an instructor as well. And so I get a certain amount of information from your responses, but that does not account for how you felt going into it, how you felt about it, was it fair, blah, 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 all those things. So, please do this. If you don't, whatever. No harm, no foul. But the more responses I get from people, the better I'm able to improve not only this course for the next test and all that kind of stuff, because I may get some feedback that I implement before the next test. Yay, I can do a better job with you all, but also future generations and things like that. So, anyway, it's worth 2 percentage points. You get it done, you get the points. It's freebies. Anyway, so there you go. There's that. I'll make an announcement with this, but this is, if you're right now, hey, how do I get to it? One, it's in the quizzes tab. Should be on your to-do list. What I'm going to do is I'm going to have a super fun time. I have to double check how this does this. You will not be penalized for not doing this. You will not be penalized if you don't do this, okay? So either it's extra credit. So you don't do it, whatever. Not going to affect your grade in any negative way. You do it, great. It gives you a tiny little boost and gives me feedback. So, take you about 5 minutes or something. All right, so there's that. The other thing I want to mention is this week you all have, instead of a quiz, I guess you could count this survey as a quiz, but you'll have a very easy assignment. This assignment serves a few purposes. One of them, again, it's one of those easy grade boosters. You put in the effort, freebie kind of thing. So it's woo all the way in. Where are you at? Homework. It's called homework, but I don't know. I don't call it whatever I want. It's called The Physics I Care About. Super easy. The details are all in here. The purpose of this assignment is I sit up here talking all day about all the things that all the physics. This is your chance to kind of connect this to something that you're actually interested in. And I do look through these. Because I'm curious what you all are interested in. It helps me get to know my classes better and all that kind of stuff. You spend as much or as little time on this as you want. The bar is very low as far as what I'm expecting. It's literally at least 2 to 3 sentences with a picture or something. You'd be shocked, but if I told depending on some of my high schools, they'd say, that's too much work. You know how it goes. But very simple. Again, you can spend as much or as little time on this. But my hope is that, you'll find something interesting and you'll kind of get sucked into it and learn something that you didn't learn that I taught you. Some connection to something you're interested in. Maybe you're into cars and you learn about how RC circuits play into, we're not going to learn about RC circuits, but how resistors and capacitors play into subwoofers in a car. Or, medical field, you look a little bit more at how the defibrillator works. Or you look at how, I think EKG, is that the one that measures the heart rate, or is that the brain one? Yeah, so you learn about the electrical signals that your brain outputs, and also your brain actually, the electrical signals in your body, how does that work? Is it like a circuit in the walls? Whatever. Lots of options. Pick anything that we talked about in test 1, and you can talk about it. You can look like how do how do the different minerals and whatever you need in your body, how do they actually go across the cell membranes? You know, it's very open, y'all. It's a very simple assignment, but my hope is that, you know, you learn something interesting from it. But I purposely made it low effort. You all just did your test. You get kind of a little bit of a break. Next week we'll have our quizzes again and all that jazz and be back at it. So, okay, any questions about this?
Just to let you know, the live stream shows a black screen.
Oh, it's doing that. Well, at least I was wondering if it would do that. Thank you. I appreciate that. They appreciate that. The numerous people that are not quite here. Well, here, but, you know, at a distance. All right, thank you. At least they got to hear my beautiful voice. For those that were on the live stream, BAM, Physics I Care About, it's in the Assignments tab. The survey is in the Quizzes tab called Survey, and I'll send out an announcement about that. Both of these things are due this Saturday at midnight. Both of these things should not take that long, so just, you know, same old, you know, basically everything's due Saturday at midnight in this class. Consistency makes it easier to remember. Okay, other big heads up. I will not be here this Thursday. I know, very sad. You will have a substitute teacher. I don't know if they call it that at the college level, but you will have Dr. Vida will be in here, and he will be going over whatever we don't finish today. So he will be covering the content. You'll get to see it. You know, it's always an interesting thing seeing how another professor teaches. So who knows? Maybe he'll do a better job than me. You'll love it. You'll say, man, I wish he taught the class. Who can say? But it'll be an interesting experience one way or the other. So, you know, class is still happening. I will also post a link to the video from last year that when I taught that section. So that'll also be available. You'll hopefully see that I'm fairly consistent in personality. I don't know. Maybe I've changed a lot over a year. Probably. I will post that video. I would have posted it already, but I realized at the beginning of the video I was also going over test 1 and had like their averages and all that stuff. Fun fact, average last year was a 65, so you all improved by 1 point something %. Yeah, but that's, I got rid of that part. So cool stuff, y'all. All right, and that was, that was just the multiple choice. So anywho, without further ado, I think that covers all the things. The next test, again, it's on the syllabus, so none of this should be super surprising, is after spring break. Okay, test 2. So we have 4 weeks of content. So we have 4 weeks till spring break, because all that also pans out. Woo, I'm excited. 4 weeks, then spring break. Then we have the test when we come back. We'll have Tuesday to review, and the test will be on Thursday. Basically the same structure, y'all. 20, maybe I'll add 1 or 2 more questions, depending. 20 multiple choice or so. Pick 1 out of 2 free response. You can expect more of the same as test 1. You know what the structure looks like now. Yeah.
Is that going to be on the next test?
Yeah, so the things that'll be on the next test, those will be in problem set 2. And as far as what exactly, let me go ahead and pull up the syllabus because it makes it a little bit easier instead of me ad-libbing it. So problem set 2, if y'all open that up at some point, that is what will be on test 2. And that'll be the next 4 weeks. So we're going to do DC circuits, magnetic fields and forces, sources of magnetic fields, and then Faraday's law. And the PowerPoints are all posted and all that stuff. And then after that, you know, let's just look at problem set 3. That's the last one. Look how tiny it's going to be. Oh, 2 things. Everything to do with electromagnetic waves and all. So we'll do like lenses, and this will be after test 2, and then the final will be all of the things. For good or for bad. So, there you go. And yeah, all the PowerPoints are there, so if y'all want to take a gander, have a go at it. All right, so DC circuits. This is kind of building on what we've talked about before. Capacitors are going to kind of, little bit, they are going to come in with actually a decent amount. Capacitors are going to come in. We have to remember they're plates, they hold charge. They're like buckets, but for charge. Resistors, what they are, literally something that resists the flow of electricity, hence the name resistor. Ohm's law, V equals IR. And we're also going to see, C equals Q over V. stuff in the last test. Remembering that current goes from high voltage to low voltage. That current is technically defined as the direction of positive charge moving, but the reality is it's negative charges going the other way. Electrons are the ones actually moving and grooving. If it was positive charges moving, that would be protons. One proton is literally a hydrogen atom. Your all's electricity is not a bunch of hydrogen atoms going through a wire. It's those electrons. So, we need to remember those things. They're going to come into play today. So we're going to talk about the junction rule. We're going to talk about how voltage changes in a circuit, how it basically goes up or down. You remember voltage is kind of like a height. That's the analogy I'm going to keep using. A voltage is like a height. And then we're going to learn how to add resistors in series and parallel, and we're going to learn how to add capacitors in series and parallel. And we're going to learn what that series and parallel means when it comes to circuits. So this is a very much application-based kind of week. Like, this is literally circuits. And when I say circuits, I mean wires and batteries and applied physics. So this is kind of like as engineering as physics gets, I suppose. I mean, obviously engineers use physics, but in like a pure physics context, whatever, we spend this time talking about circuits because they're super important. They're in everything. Every single device that you all use can basically be summarized by resistors, capacitors. Technically, there's inductors. Don't worry about those. All right, this is not something you need to know, but it's good, you know. It's one of those things. What the heck is a battery? A battery is a couple different metals with generally some acid, and there's just a chemical reaction happening that pulls the electrons from the cathode to the anode. And this generates a potential difference. We build up all these electrons on the anode. We're taking away electrons from here. So it's kind of like a capacitor-ish situation. Building up a bunch of negatives, building up a bunch of positives. Hey, we got a potential difference. Woo! It pushes all the other electrons in it. Anywho, there's videos on that. You don't need to know too much about it, but it's an interesting thing to look into if you want to. Yeah, pro tip, do not open a battery. It's filled with acid. So, but at your own risk. All right, current in a circuit. Look at these things. Wow, those look fun. We're not going to be looking at any this bad. Let's just put it that way. But I gave you all this kind of messy looking thing because there's a few things I want to point out on here. One, a resistor is a squiggly line. This is a resistor, hence the R. So that little jagged line, that's how we draw resistors. The straight lines are wires. The fact that this wire is at a corner does not mean that the wire is literally bent 90 degrees. It does not matter how a wire is bent. You know, any cable you all have, when you're charging your laptop, hopefully your wire is not super beat up. And it doesn't matter how your wire is bent or curved or whatever. Does not matter. This wire could have gone woo, and it'd be all the same. Doesn't matter. But, you know, for the sake of cleanliness, you know, we got to fit it on the page. So this corner is not literally a corner. It's not literally a corner. But you know, we got to fit it on the page, so we bend it. But it doesn't matter. I mean, think of literally every wire in your life, extension cord. No one cares if that extension cord, I mean, as far as electricity is concerned, no one's cared if it's rolled up or pulled out or bent or this way. As long as it's not broken. As long as your wire isn't broken, the insulation isn't broken. All right, great. So we have wires. There's a wire right there. There's a resistor. Sounds stupid, but it's important for us to know what the pieces of the things are. This is a battery. Some voltage source. Could be a battery, could be the wall, you know, it all depends. So your little things that you all plug into the walls to charge your phones, that is this thing. That is a voltage source. Your DC, they call them DC adapters, that little plug that you all then plug in your USB and then it goes into your phone. So this is a voltage source. That could be a battery, that could be your little thing that you plug into the wall. It is not just a battery, but traditionally we kind of say, oh, it's a battery. But it could be any voltage source. All right. And what this thing is saying, there's a bunch of things going on here. This is kind of the punchline that we're going to spend a bunch of time on. Current is constant along a branch of a circuit until it hits a junction. Voltage is constant before and after junctions. There's a bunch of jargon there that, what the heck is a junction? All right, that's our next thing that we'll kind of point out in here. A junction is where multiple wires come together. So a junction, you can think of like the English def. A junction in a road is where you can go multiple ways. So when there's a junction, you got multiple paths you can take. That's what a junction is. So that's a junction right here. This corner is not a junction. There is only one path. Sure, it bends, but when a road bends, you don't say you got multiple paths. You're going to make that bend in the road. Doesn't matter if there's a turn. A junction is where there's multiple paths it can take. Okay? So we got junctions. So what's a branch? A branch is one of those paths. A branch is one of those paths. This is a branch. This is a branch. This is a branch. A branch is literally anything before it. When it's not a junction, it's like a wire is a branch. Different branches that it can go. Okay? There's 3 branches that come off this junction. And this branch continues all the way until you hit another junction. The branch continues until you hit another junction. And then you got, more branches and more branches, whatever. So a branch goes until you hit a junction. A junction when multiple branches come together. Okay? We'll see more of this, so I'm giving you a lot of information right now. Everything I'm saying is going to get repeated several times today. Okay? So that's how good teaching works. If it's important, I'll repeat it a bunch. Current is constant along a branch. Current is constant along a branch. So let's just color this one here on the right, because I haven't put a bajillion things on it. On this purple branch, the current is the same. So if the current's here, let's just make up a number. Let's say it's 2 amps. All right? That means it's 2 amps here. That means it's 2 amps here. Oh, guess what it is here? Oh, it's 2 amps. Everywhere in that branch, it's 2 amps. Again, these numbers, I am totally making these up. Let's say this is my branch. Everywhere on this branch, let's say it's 1 amp. Oh, 1 amp there. Oh, guess it's 1 amp there. Oh, here, yep, 1 amp. Everywhere in that branch, it's 1 amp. And it all goes the same direction. Let's just say it's going this way. Let's say that this one is going this way. Think of current like a river. Think of current like a river. A river, the amount of water in the river, it's the same. If that river gets narrow, the same amount of water has to go through it. That river gets wide, the same amount of water has to get through it. Who cares what the river is doing? The amount of water in that river is the same. Unless the river joins another river, or the river splits into several other rivers. When I hit a junction, that means I have multiple rivers coming together. And if I have multiple rivers coming together, if I have 1 amp of water coming in and 2 amps of water coming in, on this third branch where they come together, let's make this guy purple. If it's coming in with 1 and 2, 1 plus 2 equals 3. Okay? So that is called the junction rule. I have a much nicer slide for that. But this messy slide, I'm kind of talking about all the ideas. I'm not going to worry about this voltage thing yet. We'll get to that one. For now, let's just focus on current. Current is constant along a branch, just like water in a river. You have the same amount of water. If that water, if the river gets wide, if it gets thin, the same amount of water has to flow through it. Otherwise, where'd my water go? The only way you get less water is if it branches. If there's another path for that water to take. So that is this first rule called the junction rule. The amount of current going in equals the amount of current leaving. So all those branches that go in, the current that goes in, they must add up to equal what goes out. Otherwise, where'd it go? If I have 100 students come into my room and only 80 students leave my room, there better still be 20 students in my room. Otherwise, where'd they go? So if this rule does not apply, like, if they don't equal, I'm building up charge at that spot, and that's not ideal. I don't know what to say there. It's not happening. They're not building up there. That is why aluminum foil is dangerous in a microwave. Not because it breaks the junction rule, but because all the sharp corners, charge builds up on them. So microwave, electromagnetic waves, makes the electrons wiggle around. On the sharp corners, they build up, and then it gets all sparky. If you put a nice smooth surface like a spoon in there, it's not as dangerous as aluminum foil. I don't recommend either, but whatever. All right, so let's just make up some numbers. I mean, you can see it down here. All the arrows, let's color code those like pink. So I got I1's going in, I2 is going in, I4 is going in, I5 is going in. All of those add up to equal what goes out. Let's make that, I don't know, purple. It's not pink, so. What goes in must come out. Very simple. Very, mathematically not too bad. You just add them up. No multiplication, no division, nothing fancy. But a very important rule. Critical to circuits. And now let's test your adding abilities. / ability to identify directions. All right, let's hit the button. Woo, didn't even crash on me. All right, so based on the image below, boom. What is the value of I4? Not the road. You got 2A going in. So current 1 is going in with 2 amps, current 2 is going in with 5 amps, current 3 is going in with 7 amps, current 4 is pointed away from it. The answer A is 3 amps, B is 6 amps, C is 0 amps, and D is 14 amps. What goes in must come out. All right, and every now and then I remember to tell you all jokes. So the joke of the day is I was going to tell you a joke about perforated paper, but it's terrible. It's terrible. Yeah. Every day, yeah. My wife for high school wrote me a big old stack of jokes, and so she curated, spent many hours finding them. So my high school was get a joke a day. If I ever forget, just remind me. Hopefully I'll remember the one. Anyway, all right. We'll close it out at 25. So 5, 4, 3, 2, 1. And again, y'all, it's just a matter of adding up what goes in. So what goes in? I got 7 amps going in, 2 amps going in, 5 amps going in. So I1 plus I2 plus I3 equals what's going out, which is I4. Look at that. So nice. So 2 plus 5 plus 7, equals 14 amps. Boom. What goes in must go out. Another one. All right, we got 6 amps we got I1 that has 6 amps. That's got an arrow pointed into it. We got I2 with 5 amps, arrow pointed into it. I3, 7 amps, pointed away from it. I4 to the right. And that's the question. What is I4? Is it 3 amps, 6 amps, 4 amps, or 0 amps? We'll go to 1 minute for this. I think we had like 88 people. We're almost there. Oh, look at that. Oh, 89. 5, 4, 3, 2, 1. All right. We do the thing with the adding. So we got 6 amps going in, 5 amps going in, 7 amps going out, mystery amount going out. So I got 6 plus 5 equals 7 plus mystery. So we have 11 equals 7 plus mystery. Mystery equals 4. I4 equals 4 amps. Boom. Very nice, very nice. Again, just comes down to, these are great ones to look at. Fairly straightforward. All right. Okay, current is fairly straightforward. Current is fairly straightforward. Voltage is that thing that gets a little trickier to understand. So remember, voltage is like a height. Voltage is like a height. When you're at 12 volts, you're at 12 height. When you're at 0 volts, you're at a lower height. And things like to go, current goes from that high voltage to that low voltage, okay? Now, clearly if I'm going from, let's say I have a battery. If I have a battery that is a 12 volt battery, that means one side is 12 volts, one side is 0 volts. And the question is, well, I start at 12, how do I get to 0? Something has to happen between the two ends. It has to go down. I mean, it goes from 12 to 0. One end's 12 while the other end's 0. Something's got to make it go down. So what are my options? How can you change voltage? First, a battery. Easy example right there. It goes from 0 to 12. It goes up when you go from left to right. So when you pass a battery, oh look, we were at 0 volts here, now we're at 12 volts here, I went up. Or, if you go the other way, you go down. So that's what you can almost think of a battery like a ski lift. It lifts people, it lifts it up. And how does it do that? Through a chemical reaction. Through that chemical reaction, there's energy in those molecules and stuff like that, and the way they react, it pulls the electrons to a place of higher energy, puts them at the top of that mountain. So raise them up, ski lift. Resistors lower the voltage. Resistors lower the voltage. So, you're going along, chugging along at 12 volts and you hit a resistor. On this side, the voltage is 12 volts. On the other side, the voltage is 0 volts. So the battery brings it from 0 to 12. The resistor brings it down. In this case, from 12 to 0. How do we calculate that? How do we calculate how it does that? V equals IR. The voltage drop across a resistor. The voltage drop across a resistor is the current that goes through it times its resistance. So hey, we got a nice handy example here. If you want to find current in this circuit, the voltage is going to be, we know it's going to drop 12. If I gave you the resistance, you could calculate the current. So that's how we can calculate the current that flows in a circuit. This is one of the ways. But this is the logic. A resistor drops the voltage. It uses some of that energy. What does it use it for? Depends. If it's just a very basic resistor, like literally the fundamental definition of a resistor, that's how old light bulbs worked. Tungsten filament. They get hot. They emit light. They release that energy as heat and light. Now, nowadays, in general, this resistor can be like anything. Anything that's using that energy for anything. We just call it kind of a resistor. But the simplest case of resistor, it uses that heat. All right, fantastic. So that's our kind of case with the battery. If we look at our capacitor, sure, we'll do black. It doesn't really matter. We have some kind of battery, voltage source. We have our capacitor. A capacitor looks like what it is, 2 parallel plates. Capacitor does the same thing. It lowers the voltage. A capacitor also lowers the voltage. So same thing. If this side is 12 volts and this side is 0 volts, everything on this side is 12 volts. Everything on the other side is 0 volts. the capacitor will have the same voltage as the battery if it's the only thing in the circuit. If it's the only thing in the circuit. Same with the resistor. The resistor gets the full voltage only if it's the only thing in the circuit. And then the immediate question is, what if it's not? Well, that's what we're going to be spending today kind of working on. But first, we kind of give you the simplest example, like everything in this class. We start with one and then we add more. That's how everything in this class has been up to this point. We started with one charge and we added more and calculated things. So, but what you need to know, batteries increase voltage, resistors decrease voltage based on the direction of current. If it depends which way you're going. If you're going, so current's going to flow in the direction of decreasing voltage. Obviously, if you go the other way, it's going to increase the voltage, but depends on what direction you're going. And capacitors decrease the voltage as well. Okay? Again, think of voltage like a height. When you hit this resistor, it's like going downhill. When you go across this capacitor, it's like going downhill. Alright. So look at that thing I just said. Voltage drops when we go across a resistor and we are going in the direction of current. Very, very important. Now, obviously, if you go the opposite way, you're going uphill now. Obviously, the opposite of downhill is uphill. So, if you go the opposite direction, you're going uphill. If you're going in the direction of I, you're going downhill. Now, I keep saying it's height. Obviously, it's not height. Make certain you all they are not the same, but it's a great analogy. I think it helps a lot understanding this. Voltage is one of those things that most people don't get. Voltage is one of those things that most people don't understand, because why would you? Unless you take physics in college because someone made you, why would you choose to learn about voltage? But it's super important. In my opinion, the stuff we're covering this week is probably the most useful stuff to you all, because everyone uses electricity. And it's probably handy to know what the heck it is, considering every device that you rely on nowadays uses it. Your 12-volt battery in your car, you need to know what that is. Another great example of why this is useful. So in your car, you all have a battery that's 12 volts, and you have an alternator. That alternator's job is to charge the battery / actually keep the car running. When your car is running, your battery's not doing much. Your alternator, you can actually disconnect your battery from the car while your car is running and it'll still work. Because the alternator is kind of doing the work. Now I say that, I don't think it makes an open circuit, so don't 100%, but I'm pretty confident in that. Now, to that end, you have a 12-volt battery. To charge that, you need to put more into it than it has. So one way you can test if your alternator is not working is when your car is running, you can measure the voltage on the two terminals of your battery, and you should be reading a voltage bigger than 12, like 14 or 13. Your alternator needs to put more voltage out to charge the battery. This is the way you can test if your alternator is bad. When you're running your car, you measure like 12 volts across the terminals of your battery, your alternator ain't good. And that's one way, I had to diagnose that at some point in my life, actually.
Where does the extra energy come from?
For the alternator? Yeah, so the way an alternator works, this is something we're going to learn in the next few weeks. It gets into how do we make electricity in the first place. So an alternator we're going to learn is a bunch of spinning magnets with a bunch of coils of wire. And when you spin magnets around coils of wire or vice versa, you generate a voltage. It's a great question. How do we actually even make voltage? The world does not run on batteries. So I told you all chemicals is one way, but it is not actually the way that we predominantly generate it. In the next few weeks, you'll learn that as well. Something you don't need to know, but it's fun to know considering all of our society relies upon it. All right, anyway, that's my little tangent. Voltage drops when we go across a resistor and we're going in the direction of current. This is a little graph that basically, again, it's like height. You got your little ski lift here. You got your battery that's increasing the voltage. Woo, I'm at the top of the hill. How exciting. You're going, you hit the first resistor, we drop some amount. Then we keep going because it's a wire. A wire doesn't change your voltage. Your voltage does not change in a wire. We hit the next resistor. Woo, I go down a bit more. We keep going. And then I hit the last resistor and I'm all the way down at 0. I loop back around and the fun continues. So this is basically what's happening voltage-wise. And there's some important ideas kind of represented here. Remember, current is the same in a branch. Current, the amount of electrons flowing in it. All of these have the same I, because the current in all of them is the same. Just like a river. A river can get wider or thinner, but the same amount of water must flow. And the drop, how much does it drop? You just take that current, you multiply by R, and boom. We're going to do that today. We're going to have a few problems on that. So this is just a nice little kind of picture showing what's going on voltage-wise. And yeah, the wire just loops back around and the good times continue. Now, I say it loops back around. Technically, this could end in something called the ground, which is just a place to dump the charge, and then the other thing can keep adding more charge, but whatever. Let's keep it simple and say it loops back around. Okay. Voltage increase, you go the opposite direction. I already said this. You're going down, if you're going in the direction of current, voltage goes down. You're going opposite direction current, voltage goes up. Nothing new here. Okay, boom, 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 whatever, blah, not a huge deal. All right, this is what I want to spend some time on now. This is where we're actually getting some math with the ideas of it. So I have a circuit here. I got my 12-volt battery. These corners mean nothing. These corners mean absolutely nothing. Because remember, no one's working with 90-degree wire. Like, we just got to fit it on this page. I could have had this go woo all the way over here and come back here. It doesn't matter. So don't worry about the corners. They're labeled ABCD, means nothing. So I got my battery. It hits my resistor 1, and then it hits resistor 2, and then it hits resistor 3, and then it returns back to the beginning. The current at every spot in the circuit is 2 amps. There are no junctions here. It is one river that is going in a loop. At no point does that river split. At no point is that river joined by another river. There is only one path from the beginning to the end. So hey, what's the current here? 2 amps. What's it here? 2 amps. Over here? 2 amps. 2 amps everywhere. It only changes when you hit a junction, and there are none. All right, so all that jazz. I is 2A everywhere in the circuit. What is the voltage drop across R1? R1, the resistance is 1 ohm. How do I get voltage from current and resistance? That's the question. And is the answer A, 1 volt, B, 2 volt, C, 4 volt, D, 6 volt? We'll go to 210. In 5, 4, 3, 2, 1. All right, so how do we get the voltage drop? Ohm's law. Ohm's law, y'all. V equals IR. If you know the current and you know the resistance, you just multiply them. So in this case, equals 2 times 1 equals 2 volts. That is the voltage drop across R1. You know what? We had so much fun doing it once. Let's get even crazier. I've got circuit here. I am now asking for the voltage drop across R1 and R2 together. What is the voltage drop from this spot here to this spot here? How much does it go down by? If you're stumped on how to do this, remember each one drops it. How much does the first one drop it? How much does the next one drop it? I got 2 drops. What's the total drop? All right, we'll go to 115. Five, 4, 3, 2, 1. All right, so we just said that the voltage drop across resistor 1 was 2 volts. No need to recalculate that. We got that covered. What's the voltage drop across R2? Well, we're going to multiply 2. You know what? Let's just write a little bit more. I times R2, which is going to be 2 times 2 equals 4. So what's the total voltage drop? You just add them. Equals 6. Very nice. Y'all are getting the idea. Looking good. All right, and to bring it all home, what is the voltage drop across R1, R2, and R3? Is it 12 volts, 15 volts, 9 volts, or 5 volts? Well, that's a problem. Thanks, y'all. But look at all that extra thinking time and all the people online saying, why are you standing around? Well, they can't see me standing. For all they know, I'm sitting. Yeah, if only. Alright, so we'll go to 45 seconds on this one. Alright, in 5, 4, 3, 2, 1. Alright, I'm going to do it both ways. There's 2 ways to answer this. Remember, the voltage, it says what is the voltage drop from here to here? We got 2 options. We could go through this whole path and calculate it. Or we could realize, hey, at this spot it's 12 volts. At this spot it's 0 volts. The voltage drop should be the same whether you're going up the hill or down the hill. But, let's calculate to prove that to you all. So V1 equaled 2 volts, done. V2 equaled 4 volts, rated that. V3 equals I times R3, which equals 2 times 3, which equals 6. So V1 plus V2 plus V3 equals 12 volts, which makes sense. If I started at 12 volts, I better end at 0 volts. It's a 12 volt battery. Fun fact, what you all just calculated was this picture. That picture I showed you all at the beginning. R1 went down by 2 volts. This one went down by 4 volts. This one went down by 6 volts. So you just did the math for that. And in total it went down to 12 volts. And then the fun continues and it goes around and around and around and around. So yeah, that's voltage. Voltage is like a height. When you go down resistors in the direction of current, it goes down, down, down. When you go up a battery, it goes up. And so on. Okay. Why did we do all that? Because this helps us understand what voltage is. Voltage, again, is a really tricky idea we got to spend time on. And what I want to point out to you all here, what's one of the main takeaways? The voltage only changed when we hit a battery or a resistor. When we get to capacitors, that too. So for example, in this corner here, the voltage along this corner is the same. Everywhere in this corner, because there's no resistors or anything like that. This corner down here, it's a different voltage, but it's the same, whatever that number is. This whole side, also voltage. It changes when you go across a battery or across a resistor. But if you're just in a wire, it stays the same. That's important. That's going to come into play when we do some things here. Because now, we got 2 setups, y'all. We're going to learn how to combine resistors in series. We're going to learn how to combine resistors in parallel. So what happens if we have more than one? We got to combine them into one. We know how to deal with one of them, so if we can just get it to one, we can do what we know how to do. In series like the World Series, one after the other. One after the other. No junctions between them. Series are the easy ones to spot. Series means they're all on the same branch. No junctions. The wire does not split across. If the wire split down here, nope, not in series anymore. These ones are, but not the other one. Okay? Series, no junctions. I can make a straight line with no, who cares if that line curves? That's all series. If it splits off, then we have something else. Parallel is a little trickier. Parallel is a little trickier to spot. If you're lucky, they literally will be parallel to each other, like this picture. But that will not always be the case. So, what is the rule for parallel? They have the same voltage on each side. They have the same voltage on each side. Voltage only changes when you hit a resistor or stuff like that. So, for example, let's just make this up and say it's 12 volts right here. When I hit a junction, voltage doesn't change. When I hit a junction, voltage doesn't change. Think of a river. A river can split into two rivers. That doesn't mean that the height went down. Voltage is like height. A river can split and it's still flat. Just because the river split doesn't mean that my ground suddenly dropped out underneath me. So, this is 12 volts. This is 12 volts. This is 12 volts. Everywhere on here is 12 volts as long as I don't pass a resistor, a battery, or a capacitor. Voltage only changes when you pass a resistor, a capacitor, a battery. Notice how these all stopped right before the resistors. Current changes when the path splits. Voltage does not. Every side of this is 12 volts. Let's just say that the other side, it doesn't matter what the number is as long as it's not 12. Sure, we'll call it 0. 0 here, 0 here, 0 here. So in a parallel circuit, how do you determine that they're in parallel? In my opinion, the best way, but it kind of requires you to understand voltage, is that they share the voltage drop across them is the same. It's 12 volts here, 12 volts here, 12 volts here, 12 volts here. They share kind of a wire on each side. That's what it ends up kind of being. Okay? Parallel is the trickier one. Sometimes you're blessed and they literally look parallel. They may not always. Give you an example. Here's a wire doing this. Here's a wire doing this. Those are parallel with each other. They share the same wire on this side, and they share kind of that same wire on the other side. You know, it kind of looks parallel, but not exactly. Let's make it even worse. Another example of parallel is I have a wire doing this, and I have one going down here like this, and those are in parallel with each other. Why? They share, you know what, I should have used, let's make it black and then I can go over it with colors. So these are in parallel. Why are they in parallel? They share this wire with each other. I say wire, they kind of share this wire with each other. They share that, they have the same voltage drop across it. This one goes from green to purple, this one goes from green to purple. The junctions change nothing. Yeah.
So, do they always have 4 junctions, or is it like more?
That's a good question. So these corners, be careful, aren't junction.
No, I know. I meant like the parallels.
No, it can vary. This one, for example, has actually only 2 junctions. The number of junctions, unfortunately, there's no. Yeah, parallel is one of those. You know, again, sometimes you're lucky and it's obvious. They literally look parallel to each other. Other times it's like this. And you know what? I could redraw this for it to be the exact same thing. I could redraw this resistor right here And it's the exact same thing. That resistor being here versus here versus here doesn't matter. A wire is basically nothing as far, changes nothing. So anywho, all that to say, this one's going to take some practice. Literally, I'm just going to be giving you all at some point some problems saying, which of these are series, which of these are parallel, just to practice this. Series, really easy. Series is really easy. Literally, they're just there's no junction between them. Nice, easy rule. Parallel, they share a voltage on both sides. The same voltage on both sides. And again, that takes time. But, all right, great. We'll practice that. What I want y'all to take away from this is what's in bold. One, you need to know what series and parallel are. In series, the current is constant. So the current in this resistor is the same as this one, is the same as this one, is the same as this one. They all have the same current, different voltages. In parallel, voltage is constant. What's the voltage across R1? 12 volts. What's the voltage across R2? 12 volts. R3, 12 volts. R4, 12 volts. Okay? Now, series and parallel have their upsides and downsides. Why? What's the benefit? One of the benefits of parallel is they all get the same voltage, which means they kind of all get the same amount of juice, you could say. That's one benefit. Another is if one of these breaks, the rest of them still work. If one of them breaks, I can still flow through each of these. Series, if one of them breaks, the circuit breaks. Christmas lights, I heard someone was telling me, oh, that's why Christmas lights are wired in parallel. False. They're not wired in parallel. Unless you spend a lot of money on them. They are still in series. If one of your Christmas lights breaks, yeah, a whole string of them is going to go out. The vast majority are still in series. Now, in one giant string, they'll have a chunk in series, and that'll be in parallel with another chunk in series. That's why when one light goes out, the whole strip doesn't, just one big chunk of it does. Long story short, it sucks. It'd be expensive to wire them all in parallel. You would literally have to have bridges across each one, and that's why I don't do it. But series and parallel, the lights in this room, if I hit a light switch and a bunch of them go off, they're in series with each other. The rest that stay on, those are in parallel with it. So there's all sorts of examples of series and parallel. Series is easier to wire up. Parallel, and it also is kind of a bit, I don't know if safer. This one will draw a lot of current, which depending on another good example of a parallel circuit. So in your house, you have a breaker box. In your breaker box, each of those switches is wired up to a certain segment of your house. I can't even say a room. Your kitchen actually has 3 breakers assigned to it. Each of those breakers, I don't know, this is such a tangent, but it's so useful that it's worth spending the time on. Because this is, again, so applicable for you all. So you all have a breaker box. It's got a bunch of switches. Let's just pick this switch here. This switch is wired up to one of the rooms in your home. There's a room. There's a room. This is what your house looks like, 100%. Whatever. Let's say this is wired up to the bedroom. Everything in that bedroom is in series with that one breaker. So when I flip that breaker, everything in that room turns off. Now, after it gets to this room, it's in parallel with something, in parallel with something else, in parallel with something else. You got all your little wall sockets. Why does this matter? Why am I telling you all this? In your kitchen, you have the most power-hungry devices, other than your air conditioning unit. An air fryer, a microwave, an oven. All of those are power hogs. They all need a lot of current. Now, your breaker has a limit to how much current it can output. Generally, I believe about 15 amps. If you are connected, we got a toaster here. You got your toaster working. That also uses a lot of amperage. You got your microwave. That uses a lot of amperage. You got your air fryer. If you try to run all of those, the junction rule is going to come into play. Let's just say that your microwave, I have no idea what the actual value is. I'm totally just making up numbers. Let's say the toaster uses 5 amps. Let's say your microwave uses 6 amps. Let's say your air fryer uses another 6 amps. That's how much amperage, that's how much current it needs to work. You add up those numbers. 6 plus 5, that is bigger than 15. It will trip the breaker. So this is something you will experience at some point, assuming you have an air fryer, microwave, toaster, whatever, all those things. I have experienced this recently in the past couple months. So if you're like, man, why does my breaker keep tripping? It's drawing too much amperage. It needs more current than it can supply. How do you solve this? Don't run them all at once. It's literally that simple. So anyway, that's a fun fact for you all. That's an example of this. Again, each breaker is set a certain amount. Your certain devices are given more amperage, like your air conditioner unit, because they need the juice. If you all ever get an electric car, you potentially will need to set up a special thing to provide it the amperage it needs, depending on if it's a fast charger or stuff like that. It may not work on a traditional breaker thing, or you may need a couple of them. How do you get more amperage? You can just take 2 of those breakers and kind of tie them together. Woo! Now I got 30 amps. Anyway, fun facts, y'all. Really, really applicable. I love this kind of stuff. This is why this class is my favorite to teach at Physics 1, because it's so applicable to things that no one knows how they work. Like, I mean, most people know a breaker box turns off things, but why? What does that A mean on it? They literally have, like, generally the amperage written on it. All right, great. Back to the mathy things. If you want to get net resistance in series, it's wonderful. You just add them. Done. So if I want to take 4 resistors and I say, man, I sure wish it was only 1 resistor, through the power of math, you can just add them up and it's as if it's 1 resistor. In series. It's a different rule for parallel, shock and awe. In series, if I want to pretend like these 4 resistors are just 1 resistor, I can. Mathematically, it works out this way. Now, why is that? It's actually not too hard to show. R net, let's just replace it with Ohm's law, y'all. V equals IR. So let's replace R net. Because the rule is the voltages will all add up. We just did that. You all did that. Like, that's how the clicker questions we just did said, hey, the net voltage, just add them all up. Great. So V net equals V1, 2, 3, whatever, however many there are. Let's replace those. We have V equals IR net. Plus for the first one, IR1. Plus the second one, IR2. Plus the third one, IR3. Plus whatever, however many they are. Hey, they all got I. The same current to series is constant. There's your proof. It's a nice, simple proof. The voltages add up, therefore, replace V with IR, and you get this. You don't need to know that derivation, but it's kind of fun to see that it's where it came from. It wasn't just out of thin air. Remember, everything in physics is from observation, and you go from there. Nothing I give you all is made up. Like, I say made up, and technically it's all made up. But, it all comes from somewhere. It all builds on something, with the exception of some stuff is just observation. Everything I've taught you in this class, if you remember, literally came from opposite charges repel and like charges attract. And literally everything we've learned has come from that. That's the one observation that was made, and everything else came from that. It's wild. It's a cool thing with physics. That's why I love it. All right, one of the reasons I like it. R net, quick check. If you add numbers, you always get a bigger number. There's no such thing as a negative resistance, so you can check your work really easily. If you have resistors in series and you get a smaller number, if you get 5 plus 2 equals 4, you messed up. It's a great check. Sounds stupid, but it's always good to be able to check and see if your answer makes sense. Okay, I believe in you. What is my net resistance in this circuit? It's the same one we've been working on, toiling on. I've got a 1 ohm resistor, a 2 ohm resistor, and a 3 ohm resistor. What is the net resistance? All right, we'll go to 55. In 5, 4, 3, 2, 1. Boom. All right. Now, something I want to remind us of here. I'm going to keep saying it because it's so. This corner means nothing. So whenever we say they're in series, corners do not matter. Junctions matter. So again, who cares? I could have actually drawn this circuit that you all see here is the exact same as this. These two are the exact same thing. Where the turns are doesn't matter. To that end, 1 plus 2 plus 3 is 6. And ohms is our unit for resistance. Woo. Fantastic job, y'all. Now the next question is why? Why am I adding these resistors together? What's the point? Okay. So what you all just did by adding those resistors together is you took this circuit, which had a 12-volt battery, and you made it this. You made it a circuit with one battery and one resistor. Okay, it's like, great, so what? Why do I care? Remember at the very beginning, I told you all, if you have one resistor, it gets the full voltage of the battery. If you have one resistor, that means this voltage is 12. I know voltage. I know resistance. What can I do with that? I can calculate current. How do you actually get current? This is how. I gave it to you all before, but now, so 12 equals I times 6. You do the math. I is 2 amps. That's the current I gave you all in all the other problems. Now you know where it came from. It wasn't made up. It's something that you all can calculate. That's why we do this. The whole point of this is so you can actually calculate the current. And then you can kind of go backwards and do all the other things that you want to do. This is the only way to kind of get the current in this. There's anywho, that's gonna be a pretty common thing that we'll be doing in these. Hey, I'll give you voltage, I'll give you resistance. What's the current in the circuit? That kind of thing. All right, parallel. It's worse. In parallel, they don't just add. 1 over R net equals 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 plus blah, 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 blah. It's not the worst thing in the world, but it's certainly not as nice. Certainly not as nice. And what I would quickly show you all is when you're calculating R net, you don't just plug them in here, hit plus sign and call it a day. When you want R net is going to be the algebra. You can kind of look into why this is yourself. It's a fun fact. I was doing this with my high schoolers today for a different equation. You're going to do 1 over R1 plus 1 over R2 plus blah, 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 blah. Okay? You can kind of see the algebra for yourself, why that is. It basically ends up being you multiply R net over, divide all the other crap to the other side. But long story short, when you want to get R net, you do 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. All right. Something I also want to hammer, like something that's also a great check. So the last check was really obvious. You add up numbers, you get a bigger number. This one's less obvious, and conceptually, it's easier to explain than mathematically. R net will always be smaller than the smallest resistor. R net, when you do this math, if literally the values of this is 1, 2, 3, 4, my R net's going to be smaller than 1. It's a great way to check your work. Why? Why is R net smaller than the smallest resistance? Here's why. Conceptually, it's easier to explain than mathematically. Remember, what we are doing here is we're taking this 4 resistors and we're making it into 1 resistor. That's what we're doing mathematically. We're taking these and saying these 4 resistors in parallel are basically 1 resistor, and we can calculate that resistance by doing the math. Okay? And so here's the way to think about these. Each of these is like a lane on a highway. I've got, a 4-lane highway here, 3-lane highway here, dirt road here, another 2-lane highway here. a car coming in has all these options. So when I combine them all together, if I have like a 1-lane road, a 2-lane road, a 3-lane road, a 4-lane road, just 4, 3, 2, 1, what is that, 6, 9, 13. I got a 13-lane highway. Of course, the resistance of a 13-lane highway is less than all the rest of these. Again, what I did there wasn't actually how you add up the resistances, but that's the logic. When I combine, it's got 4 options to take. So when you combine them together, you get a soup like, yeah, there's going to be a low resistance. I got so many options, so many pathways I can take. Each of these is a different path I can take. Some are less desirable than others. Some are more desirable. At the end of the day, if I combine them all, I have the most desirable. I got my 15-lane highway or whatever. All right. Let's see. Where are we at? I do want to do one quick practice with this. I'm going to show you all the derivation very quickly. Parallel, voltage. So voltage and parallel is the same. Voltage and parallel is the same. How do we do this derivation very, very quickly? Current junction rule, y'all. The current that goes in must go out. So if I have a current going in, let's call this I net. That's going to split into one path here. Another path, I mean, this isn't perfect, but how many colors can I use in a short period of time? Blue and purple. I already used purple. Orange. All right, so what we say is I net equals I1 plus I2 plus I3 plus I4. I'm going to leave it at 3 and call it good. All right, what's our equation? V equals IR. Rearrange this for I equals V over R. So V over R net equals V over R1 plus V over R2 plus V over R3. All the V's cancel, and that's where it comes from. That's where that equation comes from. Junction rule. The last one came from the voltages added up. This one comes from the currents added up. You do not need to know this derivation, but again, nice to see where it came from. All right, this one we'll do in 1 minute. I'll give you all a hint. There's only one answer that makes sense if you know the rule. So actually, I'll solve this one for the sake of time. While you're doing this, see if you can figure out the rule. So 1 over R net equals 1. I'm going to straight up tell you all, you can leave it as 10 kilo ohms. So 1 over 10 kilo ohms plus 1 over 2 kilo ohms. We're going to see why it doesn't matter when you convert it. They all have the same unit, 1 over 1. So R net equals 1 over 1 over 10 plus 1 over 2 plus 1 over 1. Sure, you can plug this in and get an answer, but there's only one answer up there that makes sense. R net has to be smaller than the smallest resistance.